everyone, and good afternoon. So today I'm going to talk about generating time-lapse videos from one single static image, which is basically the main part of my master thesis. This is the content that I'm going to talk about. So through this presentation, like half of the presentation, I will talk about this paper, learning to generate time-lapse videos using multi-stage dynamic generative adversarial network. But also, I'm going to talk about two other papers, which is like the most related work to this paper. So yeah, let's go. So basically, like as humans, like generating the future of, predicting the future of like an object or like a scene is really easy for us, but for computer vision still is like a challenging task. But we cannot like neglect or ignore this task due to its like challenge, because it's like it has a lot of application in like action recognition, video understanding, and video captioning. So basically the main goal that we have here is to generate like realistic long-term high quality future frames, like from one single like a static frame. So and basically this is like such a like challenging task due to like multimodality and uncertainty in content and also motion. So just keep in mind that there are two things that is really important for video generation. One of them is content, and the other one is motion, which we are going to talk about it later. So sorry. So there are two, like as I said, there are two like really mostly related works to this paper. One of them is like learning temporal transformation from time-lapse videos, which published in ECCV 2016. And the other one is generating videos with scene dynamics, which is published in NeuroIPS 2016. So first, I'm going to talk about this paper, which is the paper that we implement for the summer project. So yeah, as you can see, like the authors and the conference. So they presented three architecture in their paper, and these architecture used for predicting the future, like a future state of a natural transformation, like melting, baking, blooming, and rotting. Yeah. So through like that three architecture, the one that is like the one that is related to this paper is like this one, which is RNN GAN. Actually, in this paper they call it RNN GAN. So we have like an encoder, and we get the like feature space of the image, like the starting frame, and then use like an LSTM cell to generate like different latent vectors for different time, and then we use the decoder to generate each frame. And basically for each natural transformation, they kind of like generate 7, for each starting frame, they generate 7 like future frames. So the data set that they like published contains like, as I said, like videos for melting, rotting, blooming, and baking. So they do the query. So for gathering this data set, they do a query on YouTube API with the keywords that I mentioned, and then they use like Amazon mechanical Turk system to like ask the user to get the to choose the videos that there's no background movement, and basically the object that do the transformation is on the center of the image. So this data set is basically like object-centric data set. And as you can see, the task is somehow really easy, because mainly there is only one object in the image, and like the background is fixed. Lighting is a kind of like somehow fixed. So it's not like a hard task. So this is some of the results. So this column A is the input frame, and they use different loss functions for their architecture. So this is mean square error plus adversarial loss. I mean like column B. Column C is pixel-wise gradient mean square error plus adversarial loss. This one is pixel-wise gradient mean square error plus adversarial loss plus fine-tuning. So they do fine-tuning on the network with ImageNet, and then they do the learning. And this is ground truth. So as you can see, it somehow captured the big idea of how natural transformation happen, but still the output is small and really blurry and not that realistic. So as I said, like the main disadvantages of this paper is like although the task is really simple, but the results are not satisfying, and also it's not realistic enough. So if you see like since, as I said, like since we implement this one, if you see the image, still it's not kind of like realistic. That's okay. This is like a acceptable output. So basically, the main reason that like this, like it happened, like the output is not that good, is like usually RNNs, like recurrent neural networks, somehow like accumulate errors since each frame is made based on the previous frame. So it's a kind of like the error accumulated over time. So even like in our result, usually the first generated images are much better compared to the last generated images. Okay, so the other paper that I'm going to talk about is like generating videos with scene dynamics, which published in NeuroIPS 2016, and it was a kind of big deal on that time. So for the architect, so first of all, this is the main task, like the main task that they accomplish is video generation, not future prediction. But so basically they have like noise and they generate videos from noises. Okay, so let's talk about it. So they have two streams for generating videos. One of them is background stream, which contains like 2D convolutions. So it generates like one background that is one image that is that is like a background of the video, and it has another stream which has like 3D convolutions, and it like comes with a like foreground and also a mask, and then we use this mask to select which part of the image should be selected from foreground and which part of the image should be selected from the background, and then they have a video. But since it's like a, as I said, like video generation, so they generate from like noises, they use like an encoder, so they use like a five convolutional layers for generating the latent vector. And also they change the loss function, so it's not, so as you can see, this part is like the normal GAN loss function, but to generate the video from the first frame, they also add another term to their loss function, which is basically L1 distance from the like input image and the first generated frame, which they somehow try to make like the first generated image as close to the input frame. So for the dataset, they like basically their dataset is really famous. Like it has 4 parts, like train, babies, I remember, like beaches and golf. So they do like a query on Flickr, and they have like, I think the whole dataset is contains like 9 terabytes of data, and it's like basically 2 years of data, time-wise. So this is some of the results. So as you can see, like here for the train, they somehow like they capture the movement of the train in a way. Still, the output is not realistic, but like it seems like the network somehow capture the movement. And also for the sea, for the beach, like the waves and like the sea itself is like kind of like really acceptable. But as you can see through all of that, like humans are really creepy, because like maybe it has more kind of like dimension compared to the like train, and also because we also have a lot of like limits and constraints, so maybe the network cannot capture all of that. Okay, so the main problem of this paper is like the output is blurry and it lost a lot of content details. So they think probably it's because like in vanilla encoder decoder structure, we are going to lose a lot of details through this like encoding and decoding process. So right now I'm going to talk about like the methods that they presented in this paper to overcome the disadvantages that we talk about. So okay, this is the overview of the paper. So this is basically it's like a V2V kind of architecture. So they use two networks, one of them for generating content, and the other one is for generating the motion. So basically they mentioned in the paper that they thought it's not possible to capture both content and motion with one network. So so basically they use two networks. One of them is called BaseNet for like capturing the data distribution of the content, and there's another network for capturing the data distribution of the motion. Okay, so let's talk about each one of these networks in more details. So the first one called BaseNet. So so they use like a 3D unit-like architecture. So it means that they have some skip connections between encoder and decoder. So when they get the input, like the first frame, they repeat it 32 times, which is the number of frames that they want to generate, and then they give this video to the like a 3D convolutional network, and then they generate the video, and they give this like a generated video and real video to the discriminator, which is like basically like the GAN, like typical GAN that we expected. And also for loss function, they use two, like the loss function has two terms. One of them is adversarial loss, and the other one is content loss. And they mentioned that they use L1 distance instead of L2 distance for content loss, because L1 distance usually provide like a sharper output compared to the L2, but probably it will be slower. Okay, so the second stage, like the second network that they use for capturing the motion distribution is called like RefineNet. So as you can see, like so it get the output of the BaseNet, and so the structure of the networks are really similar, as you can see. Like they just only like remove some skip connections, and so basically if the networks are the same, we suppose that like they through the learning process they become like identical, because they want to do everything is the same with them. So what they do for learning the motion, they actually add another term to the loss called like adversarial ranking loss, which I'm going to talk about it in detail. So for the motion feature representation, they use something called gram matrix, which gram matrix is basically like used a lot in dynamic texture synthesis, but here they use it for motion representation. So okay, so just imagine like H of L and Y is the output of discriminator for layer L with input Y. Okay, so like the dimension of this like output is N by CL by TL by HL by WL, which N is the batch size, CL is filter size, TL is the number of frame, H is height, and W is the width of the image. And then they reshape this matrix to this one, like H hat, which the dimension is N by M by S, and so basically S is like the multiplication of these two values, and M is multiplication of these two values. And then gram matrix is like this, something like this. So they multiply. So for okay, so since here we have a new term called N. So this N represents each sample in the batch, in our batch. So for each sample in the batch, we compute like H hat and the transpose of H hat, and we multiply these two and like multiply by this coefficient. So this will be the gram matrix for layer L. And to compute like adversarial loss. So what they have, I mean adversarial ranking loss. So what they have in their mind is they want to like push the network to generate an output, which is Y2, to be as far as Y1, which is the output of the base net, and as close to the Y, which is like the ground truth. So they use like this term. So basically this is like the L1 distance of the generated video and ground truth same, and here is like the L1 distance of generated video and like refined net video and base net video. For so this term is only for layer L. So so they like do a sum over for all of the layers, but actually in the paper they don't sum over all of the layers. They only sum over like the first layer and third layer, but just like for the annotation. And then like the loss function for the second stage network will be like this. So still they have content loss, adversarial loss, and they add like a ranking loss with the coefficient. And actually they put 1 for this coefficient in the paper. So this is how they try to like make different between the base net and refined net. Everything's okay. Okay. So maybe it's good to mention that actually, like as I said, like gram matrix is not their contribution. So gram matrix is used in like dynamic texture synthesizing, but the contribution here is that they use a different way. They do a different way to calculate gram matrix, and also it's like it's like future prediction, not like dynamic texture synthesis. So in like the dynamic texture synthesis, what they do is that they train a VGG19 network, and then they extract the output of each layer for the texture synthesis. But here they actually use the discriminator itself to get like the motion. Okay. Okay. So let's go for the experiments. So this is their data set, and so they also do a query on YouTube and get like the sky like time lapse. So as you can see, the movements are dynamics, and they have different lighting condition, different weather condition, like night, day, aura, and everything. So it's basically like a dynamic range of different motions. But all of them are clouds. So it's like they also mentioned that for this, like they cannot do this kind of motion movement for different kind of different entities. So they only focus on the clouds for this paper. So this is the details of their implementation. So they use PyTorch. Actually, they don't mention that they use PyTorch, but when I checked the code for the dataset, it was PyTorch. So I just guessed that, okay, probably it's PyTorch. So they use Adam with this value. As I said, the lambda is 1. They use batch normalization and leaky ReLU for like the 3D convolutional layers, and batch normalization and normal ReLU for like deconvolutional layers. Identity mapping as a skip connection, and like this is okay. And like this is their like configuration for the network, like the encoder and decoder. Yeah. So they presented two kind of like result, qualitative result and quantitative result, which we are going to go through. So as you can see, this is the input, like the input frame, and they compare the result with VGAN, which is the one that has a mask, RNN GAN, which has the LSTM, and a stage 1 basenet and a stage 2 refinement. So as you can see, for VGAN and RNN GAN, the result is like kind of not satisfying, even compared to the input. With the second stage, actually each frame has a kind of like, each frame individually like seems really realistic, but there's no motion. But in the second frame, it's realistic, and also there is a motion. So if you want to see it, if there is a motion, I don't know if like obvious. So there is a distance between this cloud and this cloud. There is a like empty space here. But as you can see here, they overlap each other. So that's like, maybe it's because only like there's not that much fun, but yeah, it's kind of, it has a movement. I will show another video that shows like totally the movement. So this is their second qualitative result, which they want to show that, okay, second stage is necessary for this purpose. So still, as you can see, so this is the stage 1 basenet, this is stage 2 refinement, and as you can see, like, we don't have that much movement here, but here there are many changes through the time. Also, like for this one and this one, the clouds are coming, so it's like kind of obvious that their method is generating something. So I think this result is really obvious about like the efficiency of their method. So this is the output of their method, and this is the ground truth. So it's like each ground truth is like, so this one is for this one. So basically, each one of them is like the ground truth for this. Yeah. So, and as you can see, some of the results are really interesting. Like, if I can find, so for example, here seems like a realistic movement, but if you see the ground truth is totally different, or in some cases, so the direction of the movement are different. So like, if I can find, okay. So here there is like movement to this direction, and this one movement through this direction. So it's kind of like capture like the movement of the clouds in a way. Okay. So let's go for quantitative result. So, so for the first part, they ask like workers on Amazon mechanical torque system to. So they show 2 videos generated from 2 different so videos generated from different algorithms, and also like real videos, and ask the user to select which one you prefer. And as you can see, most of the users prefer like their method over VGAN and RNN GAN. And also here, again, they want to show that second stage is like helpful. So they actually compare first stage to second stage. And also, as you can see, like second stage is really necessary for their purpose. And this is like the last quantitative result. So they use like normal image measurement unit, like mean square error, peak signals to noise ratio, and similarity structure-based image measurement. So in all of them, they're met. So also they do this experiment on beach dataset and golf dataset, which is presented by the VGAN. And in all of them, basically they have like much better result. Okay, so for the conclusion, basically this paper has 3 contributions that we cover. Like the first one is the data set that I provide. So it's like a high resolution, dynamic kind of movement data set. And also they present like a new architecture called multi-stage dynamic generative adversarial network, which can capture like spatial and also temporal information and generate like high resolution images from one single static image. And finally, they use gram matrix for motion modeling, which is like, as I said, totally like different kind of like application compared to the previous application that they used. And they kind of use it for like to produce realistic movement for like the generating videos. Yeah, basically this is it. Any question, comment? Yes. Okay. Actually, it's really kind of simple GAN training. So they train the discriminator and they train the generator. But the only thing that is different, they add also the ranking loss to their like loss function for the discriminator. So it's basically the same. No, it's not like a it's like a simple GAN if we can say that. Actually, they don't mention, I start doing, so at the beginning I start with 64, but I ran out of the GPU, and then I start from 2, and until 32 it's fine, but from 32 to 64, yeah, I cannot do. So right now what I'm doing is like I use batch size of 32. Yeah, batch size of 32. And and I train, once I train it for 6,000. Also, they don't mention how many epochs they train. So first I trained it for 6,000 epochs, and the result was a little bit like weird. So since I have the presentation and my system has a lot of time, so I run for 12,000 generation, and I want to see what will be the output maybe next week. Yeah. Any other comments, questions? Okay, thank you. Thanks a lot.